Today we'll be making this fractal in geometry nodes using Blender 3.3. It's made up of a single geometry nodes modifier with two major parts. The first part is this outer network that you see here, and the second part is this inner fractal iteration network. The third part of this tutorial will go through the shader nodes for the fractal, which shows a relatively simple setup that uses an attribute that we create in the geometry nodes to govern the colors of all the points in the fractal. So to begin, let's go through that outer network. Now, the way this network works is it starts by initializing a single point with a mesh line mesh primitive node with the count set to 1. So instead of being a line, it's just a single point. We initialize the scale attribute, which we're going to use in the fractal iteration, and it will get transformed in these nodes and then govern the scale of the output points, and that scale is then output in the group output, so we can use it within the shader nodes to create the colors of our fractal. So let's visualize the way this works a little bit. What I'm going to do is I'm going to disconnect the group output so that we can look at every step of the process. So let's hide these two directional lights and start with these sets of initialization nodes. I'm going to pipe that into the group output, and I'm also going to bring in a mesh to points node so that we can see that a bit easier. So as you can see, we've just got a single point at the world origin. We're also initializing the stored name attribute for the scale attribute, and we're initializing that to a value of 1, and it's a float type in the point domain. After that, we'll start going through the fractal iterations. And so generally what this fractal iteration node group does is it does a transformation on the point, which includes a translation and a rotation, and then it mirrors or inverts the point across all three axes. So you'll see in this first iteration that if we take this point, we translate it in a direction, maybe straight up, and then rotate it by a certain amount, then we get this point. And then if we mirror over all three axes, we'll get all the rest of them. So mirroring over the z-axis would give us this one, and then over the y would give us this 2 to create these 4 in the back, and then mirroring over the x-axis we'd get the additional 4 points. Then this node network joins those new points with the original point, and you get what you see here. So we've got a total of 7 iterations, and as we step through them, you can see the fractal start to form by having these successive transformations and inversions or mirrorings on the output of the last iteration. So we'll just quickly step through those to see how the network evolves. And you'll see that these look a little bit different than the eventual output, and that's because all of these points have the same scale. And this brings us to the last part of this outer network, where we convert the mesh to points like we're doing for this visualization, but we also pipe in this value into the radius input, which scales all these points by an amount that is governed by the scale attribute that we initialized in our original initialization nodes and gets transformed throughout the fractal iterations. And what that does is it changes the scale of each point based on essentially which iteration it's involved in, because this attribute gets divided by 2 or multiplied by 0.5 actually in each fractal iteration. So then the last part of this network is just setting the material. And so we set that to this fractal material that I've created, put that into the group output. I'll delete this visualization node. And then we want to make sure to pipe in the scale attribute back into the group output so we can get the appropriate coloring. Okay, so moving on to the inner fractal iteration network. And the way this works is that you take in your group input, which is a collection of vertices or points. Then you translate and rotate those points. You transform the scale attribute, and then you perform your inversions or mirrorings across all 3 axes. So step by step, take your input, translate that input using this transform node. That is transformed in the up position, just global z, by a value of 0.5. And then, after you do that translation, you rotate that point using this vector, which is artistically defined, but it only uses the x and y component. You don't rotate by z at all. If you did, you'd get some different outputs. In fact, let me go into this outer network and remove one of the iterations so that this becomes a little bit more interactive in terms of a preview. So you can see that changing these rotations will change the behavior of the network. I'll set that back to 0. But you can see in this frame here I've got some animation nodes set up. And so that's as I press play, you see the fractal transforming, and it actually loops every 500 frames. So you don't need to have that animation here. These could be any points. If you rotate by just the x-axis, you'll get this sort of two-dimensional fractal, but it's definitely more interesting if you do it along multiple axes. So then what you do is you scale the scale attribute by the same amount that you scaled the translation by. So that's 0.5 or half. So the way that you do that is you bring a named attribute input node, you set that to the scale attribute, you multiply that by 0.5, and then you bring in a store named attribute node and you restore the scale attribute by that new value. And so then what that does is that every time you add one of these fractal iteration nodes, the attribute for the new points is half of the old ones. And the old ones remain the same because you'll see that we also bring this geometry input in this upper line here, and at the end we join the geometry. But in this path there's no transformation of the scale attribute. So that remains the same for all the points that are not created in this inner fractal iteration node. So after we store that scale attribute, we just perform the inversions. So The way this is done is just with a transform and a join node. So we take the original geometry, and we want to keep that, so we'll put that into this join geometry node. But then we also, on a separate path, transform that geometry with a scaling where x and y stay the same, but z is -1. So whatever axis you're mirroring over, you're going to set that axis to -1. So this one is z, this one is y, and then this one is x. So you do those 3 inversions or 3 mirrorings, and then you join those outputs with the output of the original input, and that's the end of this network. So then you create however many iterations you'd like. There are 6 here. Originally I had 7. I'll put that one back in. And the last part is to go through the material which governs the colors of this fractal using that same named scale attribute. So we've set the material in this last node of the geometry node network here, and it's set to a material called Fractal, which I have created. And if we go into the shader editor, we can see the nodes for that. So the basic way in which this works is it takes in the scale attribute as an input. It does some transformations on that, converts that value to a color, and then uses that as the output to this principled BSDF shader node. Now, these colors are entirely up to you. You can have a lot of fun with them. These transformations are just sort of artistically created. They aren't based on anything mathematical or particularly robust. It's just what I thought looked cool. So I'm going to delete these, and then we'll start from the basics. So the absolute most basic form of this would be to just take this attribute and put it into the base color slot of the material. And this visualizes that attribute pretty well. So what you can see is that these inner nodes, or these inner points of the fractal, the larger they are, the lighter their color. So this very, very first point, which has a scale of 1, is white. And then as you go through each iteration, they get successively darker until you get to a full black color. Or you actually never get to the full black color because you're dividing by 2. So it just gets closer and closer to 0 infinitely forever. So if you want to play with colors, one good way to do that is to bring in a hue, saturation, and value node, and then pipe the attribute into the hue slot, set the color to something with a little bit of saturation to it, and then pipe that out into the base color slot. And so if you move around this color, you can see the transformation of the hue by scale will change the colors. And so then you can start playing around with how much this factor changes the hue. And since there's this effect of the scale attribute dividing by 2 each time, it's not a linear transformation. And I actually want to make the color change a bit smoother across the different levels, or in a more linear fashion. And so the way that I'm going to do that is I'm going to bring in a math node, and I'm going to set it to power, bring the factor in, and I'm going to bring that to a pretty low amount. And so now you can see that the colors change a bit. And I'm not going to get too technical here because, quite honestly, I don't know all of the details. I'd have to think about it. But this is for fun. This is art anyway. So just play around with the values and find something fun. That's the whole point of this. So if I set the exponent higher, the change is going to happen. The gradation is going to happen much faster. So you definitely want this exponent to be low. I'll go to 0.1. I kind of like this effect. And then what you can do is you can multiply it. So now that I've got the curve or the rate of change of the color a little bit closer to what I want, I can change the scale of it. And if I want the colors to change really quickly and get this almost rainbow type effect, I can just multiply by a lot. Let's say 100. And then I can always go back to this color input and just sort of move around the hue wheel to find the color that I want, as well as the saturation. And so you can also control the saturation this way. So if I want points with a scale attribute that is higher or lower, I'll have less saturation, and higher I'll have more saturation. So that means that the larger points will have a saturation closer to 1, and the smaller ones will get closer to 0. If I want to invert that, I can multiply and add -1 and 1. Actually, this needs to go in before the power node. So if you do that, then the largest points will have a saturation of 0. The outer points will have a saturation that's higher. So you can just play around with this as much as you want and just find something cool. And I just thought of something that I would like to try, which is to make a certain level based off of the scale, so a certain level of the fractal, a certain iteration level of the fractal based on this scale attribute, emissive. Because I just think that would look cool. So the way that I'll do that is I'll bring in an emission shader as well as a mix shader. I'll mix these together, and then I want to make sure that the factor singles out one level, or the factor, if I said that right. I think I did. Maybe I said fractal, factor, fractal, I don't know. Singles out one level of the fractal based off of this scale attribute. So we'll use a math node. Make that compare. Bring in the factor. And so let's think about what level we want. If it's level 1, let's set the epsilon. So this is the epsilon is basically the amount of leeway you have between the input value that you're checking and the value that you're checking against. So if my value is at 0.5, then anything between 0.5 and 1.5 will go out as 1. And I want that to be a lot lower, so I'm going to set that to be, let's just say 0.1. So if I've got this value set to 1, then that single inner point is going to draw from this emission shader, while every other point is going to draw from this principled BSDF. Let's pump up the emission And if I want to go to the next level, we know that this factor, or this attribute, the scale attribute, in each successive level is divided by 2, or multiplied by 0.5. So 0.5 will bring me to the next level. If I divide by 2 again, I'll get the level after that by 2. Ooh. Do I want that level or this level? I think the next level. But maybe not so emissive then. I don't know. Here, and then let's pipe in the same color that we have in the other shader into this one. So then that way, let's see what happens if we do that. Yeah, so I actually want to set my epsilon to be a bit lower, because as we keep dividing, the difference between levels becomes lower. So this epsilon should actually be as low as possible. Ooh, I like that green. So let's actually bring this strength back up. And then maybe I'll bring the value of everything here down. Maybe we can turn off the directional lights. Maybe just keep one of them on. Anyway, I could mess around with this for hours, but I will spare you. I hope you enjoyed this tutorial. I hope it's been fun. I hope you learned something. And I hope you continue to mess around with Blender, because it's a blast. And I enjoy doing it. I hope you do too.